Terracini speaking on a priori regularity equations generating sets.
Okay, thank you very much. So first, I'm very happy to be here. And actually, my talk will be a bit more PD than spectral theory. But most of the motivations, or at least some of them, are quite connected with spectral optimization. And also, I think that some of the main ideas, which I will try to explain, are related with some rigidity properties of solutions of rather simple PDEs, the Laplace equation to start with, and which I think are of some interest and also are also related with some spectral properties. Okay, so let me start with, I will also talk of other kind, let's say, a more general class of differential divergence form differential equations. But to start with this, we take the Laplace equation. Okay, so we take the Laplace equation. Okay, so we have a function and the Laplacian of u is equal to 0 on some domain. Okay. Well, there is a lot of work and very nice properties also related with the spectral theory about the nodal set of a harmonic function, or to solutions of more general divergence form differential equations, like this one. Okay. But one very, if we look at the regularity properties of the harmonic functions, then there is a very important property, which is, let's say, a slight restatement of the Liouville theorem, which is the following. And in fact, one can build all the regularity theory for Laplacian and other divergence type equation on only one property, which is the following. If you have a solution u, which grows less than linearly at infinity, so if you have an entire solution, we will be, okay, so Liouville theorem, let's say Susanna's version, because this is, okay, if u is an entire harmonic function, which grows less than linearly, okay, so say that u of x is smaller than some constant 1 plus x to the alpha, and alpha is between 0 and 1, then u is constant. Okay. How to prove such a statement? This is not the usual way of doing. You just take Cauchy representation formula, and then for the derivative, okay, and then you see that if u grows less than some power alpha less than 1, then the gradient of u must be constant. Okay, so you just see is couple of lines proof. Okay, and if you like, if you like this way, you can build all regularity theory from this, and also from and now, but very often in shape optimization or other free boundary problems, so shape optimization with the volume constraint. One part of the theory is to have regularity up to some boundary, but you don't know the boundary. Okay, you know very little of the boundary because the boundary itself is a part of your problem. For example, assume that you want to minimize some eigenvalues or some combination of the eigenvalues on domains having a fixed volume. And assuming that the extremal, the minimizer exists, then you want to say something about the regularity of the boundary. The regularity of the boundary, of course, is somehow related also to the regularity of the eigenfunctions. And one maybe technical stuff is to compare different harmonic functions which have a common property of annihilating along a boundary, and this boundary at the first glance has very little regularity. Okay, so in general there is something which is called the boundary Harnack property. Okay, which says that if you have two harmonic functions, okay, on let's say B1 intersection time omega, okay, so you have something which is like this. You have omega, and this is B1. And you know that d omega is well, not C1, not even Lipschitz, but even a lower regularity I will not discuss here, which is called the non-tangentially accessible property. Okay, which is really a very, very mild regularity requirement of the boundary, which is very natural when, for example, your set is has some extremality properties with respect to for example, fixed volume variations or so. Okay, and you know that, let's say that U is positive, then U, V, and both U and V are 0 on the boundary. Okay, so if you have two functions which are 0 on the same part of the boundary, and one, let's say, U is positive, then V over U is C0 alpha of omega, of this up to the boundary, okay, of omega intersection B1. Okay, so this means that harmonic functions have a common way of approaching the boundary when they go to the boundary. Okay, and this is sometimes very, very useful in for starting some regularity free boundary theory in many variational cases, for example. Okay, so this is something that has been used and this property of non-tangential accessibility has been stated by Koenig and Toro, for Jerison and Koenig, for example, and used in many situations, and it is known to be valid also for general divergence form operators, provided the coefficients are reasonably continuous. For example, Hölder continuous themselves. Okay, and now there is another motivation, actually, which is, okay, let's say that in this case we have that U is 0 on some set, and V also. Okay, so the point is that U and V are 0 on the same set. Here we are considering a kind of one-side problem, okay, because our omega is here. But we could consider the case that we have two functions which solve the very same elliptic equation, and we can take their quotient. Provided, of course, there is the second one, V, is 0 every time the first is. Okay, so the idea is to consider two solutions, let's say two harmonic functions, okay, on an open set, okay, on B1. And we assume that the 0 set of V, okay, this one, includes that of U. Okay, may happen, may happen. What can you say that about V over U? Okay, and how much this property that I will have to specify in a moment, for example, depends on the smoothness of the coefficients of the matrix A, if any, and so on. Okay, I'm not talking about how to find a pair of functions which are both harmonic on the same ball and that they share the same 0 set. In fact, I don't have any constructive way of doing this, but assume that we do have such a pair. Okay, well, there are two very important papers by Logunov and Malinnikova in the, it is already now 10 years ago, 1914, 14 and 19, sorry, 19. I'm really 2014 and 2015, which says that this ration is actually analytic. Let's say. Okay. This is a very interesting fact itself, of course. So we were trying to extend maybe not so much this result, but even weaker results, like having kind of estimates on which are C1 alpha, C0 alpha estimates, C1 alpha estimates, also depending possibly on the regularity of the coefficients A, and also which are uniform with respect to the nodal configuration of U. Okay, so this is a first problem, uniform. Okay, so first let's go in C k alpha, k equals 0, 1, or so, and also that this could be, this estimate as uniform with respect to the nodal configuration of U. Okay, so we should have a class of possible nodal configurations of U, which is, let's say, contains more than one element, just to say, and where there is enough structured compactness to make operation, and then that this estimate, we wonder whether this estimate, if any, can be made uniform with respect to the nodal configuration. Let's say that we were it's a local estimate. If you solve the equation in a larger ball, half the radius. Yeah, yeah. Okay. Actually, let's say that this is a sorry. It's kind of professional deformation. It's you start with the local estimates. Okay. So you know that you are solving a problem in a bigger ball, and then you can solve in a small. You have estimates in a smaller ball. Okay. This is not the very okay. So okay. Especially when you are in Hölder spaces, this means that the bound in the Hölder space of the ball of radius 1/2 is actually bounded with respect to the L2 norm in the larger ball, just to say, or other. Okay. So first, okay. So this is the topic. Yeah.
Instead of harmonic functions, I was interested in eigenfunctions of the function.
Okay. Yeah, of course, this maybe, if you like, is the same as adding some matrix. Is a kind of realm of perturbation, problems which are locally deformation of the Laplacian. Okay, these are local problems. Okay, they are not global. So I'm just taking a yeah, this instead of here you may have some v of x u with v whatever, basically.
And for the other equation also, right? You could have.
Okay, yeah. Well, in principle, you can have the same. It's not really necessary to have the same equation, but having the same equation makes things easier to be stated.
But the positive definiteness of the operator is not necessary.
Well, what I'm saying is that these are local properties. So I'm in a class of operators which become positive definite when you localize in a sufficiently small.
Because it's a small compact perturbation.
Yeah. That's the point. That's the point. So you can in fact add a number of lower order perturbation, and the result will be the same. Okay. So in principle, so this was done by Logunov and Malinnikova in 2 papers. Okay. And what I'm going to talk about are related with some papers I published with 2 with Sir and Vita, and 2 with Dotton and Vita. So there is a number. Okay, let me just say one thing about this Logunov and Malinnikova result, which is also related to some property that may be seen as from an algebraic point of view, but also from the point of view of some Liouville theorem, if you like. And this is what is called the Murdoch lemma, which dates back to 1963, which says if you have P and Q 2 polynomials, okay, in polynomials, so it's something global, and you know that Q is harmonic. Okay, and you know, so this will be in the denominator, and the P, the zero set of P includes the zero set of Q. Okay, so this is what we call the V, and this is what we called U before. Okay, then Q divides P. Okay, then Q divides Okay. Okay. And believe it or not, we can associate to such a statement a Liouville type theorem. Okay, and I will do this during this talk. Anyway, this is in fact something which is maybe known more to algebraic geometers than to analysts. In any case, you don't need, you can also take any fixed coefficient divergence form because they are all actually all equivalent. Okay, so okay, let me make another observation. Okay, assume that you have two functions, two solutions of the same equation. Let's take this Laplace equation just for simplicity. And well, we are interested in the regularity of the quotient. Okay, so we take W is equal to V over U. Okay, and U is may annihilate somewhere, but when it does, also V will do. Okay. So we have an equation also for W, which is a weighted equation. Okay, solves a differential equation, a divergent form, with a weight which is exactly U squared grad W equals 0 on the same set as before. Okay, so one possible attack strategy for proving any type of regularity of this quotient could be to look at this new differential equation, which is solved. This is a very simple computation, and look whether we can say something about the regularity of this other equation. Okay, so now let's say that to simplify, we go back to the boundary Harnack principles, and we have, let's say, a part of the boundary, and now we have U is positive here. This is omega. U is positive, and we are working on this side, and we look at this equation, and we know that W, that the coefficient will, this is a degenerate equation. Okay, it's a degenerate equation, and so it also is not very much clear what is the boundary condition which will be satisfied by this ratio. Okay, well, first it's not even clear how to what is the natural boundary condition for this problem. If we reasonably, this would be Neumann type boundary condition. Okay, so for example, we can say if there is any boundary, exterior boundary normal, then we can associate, something like the limit when x goes to the boundary of U squared grad W times nu equals 0. This is very cheap, you know, because U itself is going to 0. So it is not so, let's say, so difficult to meet this boundary condition. Okay, what is the problem? Well, here we enter in the realm of weighted regularity for weighted PDEs. This has been studied and the various conditions on the weight. The problem is that these, which are related to some properties associated weighted Sobolev spaces. If you have good embedding of this weighted Sobolev space, then you can try to build up some regularity theory in a, let's say, reasonably standard way. Okay. The problem is that, as happens, this weight does not belong to this. These are called Mackenhaupt classes of weights that grant regularity, for example, Elder continuity of the solution. Okay, so for this type of equation, no general regularity theory for weighted elliptic equation is available, and this is maybe why people working in this field always have disregarded this equation. But of course, we are not reasonable people, so we started look. Okay, but this is so in general we could try to look at the equation y power 2, because there is also a big field of interest in weighted singular degenerate or singular equation, which is related to fractional power of operators and Dirichlet to Neumann operators. So you add one more dimension, and then you can define the fractions of the Laplacian as solutions of some Dirichlet to Neumann operator. So in general, this type of equation, let me say maybe in one specific way, let's take the positive half space. Sometimes you have one dimension, one more dimension, and then here you have one harmonic function, which is standard, which is the linear one. Okay, so let me think that this is xn plus 1, and I call it y. Okay, and then you look at solution of this equation, divergence of y to the power a grad w equal to 0 with, okay, maybe some Dirichlet boundary condition, w over Rn, this is Rn plus 1 plus, this is given. Okay, and this problem, so the Dirichlet to Neumann operator is actually some power when A is between -1 and 1. Some power, fractional power, and now I cannot remember, is S is 2A minus 1 probably, or something like this. Okay, anyway, so there are some various reasons for looking at this type of problems. Okay, and so okay, so this is to motivate indifferent. So now we can try to consider this type of equation on a one-side domain. Okay. So the easy part, which may not be so easy, but it is to start with, is one-side domain. This means that the domain is on one side of the boundary. Okay, so here we have omega, and here we have the boundary. Of course, we may also think of other situation. For the problem of nodal domains, we actually have an equation on both sides of the so because the this is the nodal domain of one of the two of the denominator. Okay, but to start with, we assume that somehow there is no larger solution U of which this is the nodal domain, but we know that so gamma is given is not a free boundary. Okay, so in this case, okay, we can try to look at the regularity of this type of equations. So in general, so we assume that we have an equation of this type, u to the a, u is positive. Then we have some matrix, A of x grad u, okay. And now we look at solutions to the Neumann boundary condition, okay. X goes to the omega of u squared a grad times mu equals 0. No, and a is something which is larger than -1. Ah, okay, sorry, this is u to the a, of course. Okay. This is very restrictive, is a is negative, and is less restrictive, is a is positive. And so we assume that, so we have a theorem which says the following, okay, which basically says that this operator with this boundary condition is strongly elliptic. Okay, if you forget of this weight, and okay, so A is uniformly elliptic matrix with variable coefficients, of course, and we assume that A is in C0 alpha of omega. Okay, so it's okay, so if we had no boundary, if we had no okay, and also we assume that gamma is, which is the boundary, is C1 alpha. Okay, so if we are C1 alpha here, and u, what is u here? For us, u is C1 alpha. C1 alpha, C1 alpha function such that u is positive inside, is equal to 0 on the boundary, and if we don't ask anything more, we assume that the boundary derivative is negative. Okay, this is obvious if u was so u is basically nearby. It goes like the distance to the boundary. Okay, we don't really even need that u is a solution of anything. A is between -1 and infinity. Okay, what is a solution of this? This is a critical point of the associated Dirichlet energy with no boundary condition. Okay, then W, the solution is okay, is what? No weight, Schauder estimate, C0 alpha coefficients. Solution is C1 alpha, increases by 1. Okay. Well, this is exactly the same. So W is C1 alpha, okay, of omega up to the boundary, of course, of omega intersection B1/2. Let's start as usually in omega intersection B1. Okay, and this is in B omega intersection B1. And note, and this may be of some interest, that and especially when A is positive, which is more or less our case, and then that A grad W times nu is equal to 0. So there is an associated Neumann boundary condition to 1, to 1, without the weight on the omega. Of course, intersection B1 half. And this makes sense because now we know that W is C1, so C1 alpha. Okay? In principle,
check that I understand. So when you write Hölder space 0, 1, 0 alpha, 1 alpha, omega, you mean omega closure of omega, right?
Yeah, okay.
So you mean that it's up to the boundary, it does not.
well, when it is when I only write continuous, I don't I need to distinguish interior continuity and up to the boundary. But if I have Hölder continuity with in an open set, this will also go up to the boundary.
But if it's a norm space, if you
This is a normal space. Okay. Yeah, this is considered as a norm space. Sorry, I didn't. And what is the solution? A solution, I mean something which is W is in H1 with is in H1 of let's say B1 intersection omega with weight U to the A. Okay, U is positive, which solves in the sense that for every other for every test function, the integral of U to the A grad U times grad phi is equal to 0. Okay. So this is our first theorem, and also if we wish and we can increase regularity here by k, so we start with something which is coefficients which are of class ck alpha and boundary ck plus 1 alpha, then and u ck plus 1 alpha, then w is becomes ck plus 1 alpha. Okay, which is okay, which is in fact something more. If we think when A is equal to 2, okay, then W is equal U over V over U. Okay, and assume that U and V are solving the same equation. Okay, so we go back to the initial problem. In this under this assumption, the usual Schauder estimate, higher order Schauder estimate, say that if A is ck alpha and gamma is ck plus 1 alpha, then U and V are both ck plus 1 alpha. Okay, so in general, if they are both non-degenerate, the quotient will lose, V over U would lose 1 degree of regularity because they are both going to 0. But here, the miracle is that this, in fact, does not lose anything. Okay, you can go. So that this problem is really elliptic, and the usual Schauder estimate of higher, basic of higher order are all satisfied. Okay, let me say something about how to deal with this class of problems, how we dealt actually with this class of problems. Well, this this type of estimate were obtained by scaling method and blow up. And so you assume by the well, first you can regularize the problem by saying, okay, instead of having a weight rho, which is u, okay, and then you take rho to the a, you regularize by taking another weight, which is just u squared plus epsilon squared, okay, and then you go to an elliptic problem, okay, an elliptic Neumann boundary condition problem, and then you can solve, and you have the usual regularity theory up to the boundary. And then what you can try is to find estimates which are uniform with respect to the regularizing parameter epsilon, and try to go to the limit. And you succeed basically due to one nice Liouville type estimate, which is the following, okay? Liouville type theorem. Okay, which is the following. If you have a solution on a half space of this problem, okay, 1 epsilon square plus y square to the a over 2 grad u is equal to 0 on a half space with Neumann boundary condition. Okay, so with, let me write this way, even goes to 0 of epsilon square over y square a2 du over d y is xn plus 1 equals 0. Okay, if you have an entire solution of this Neumann boundary problem, and you know that u grows less than linearly, then it is constant. Okay, and if you know that it grows less than some power, then it is a polynomial in the remaining variables, an harmonic polynomial on the remaining variables of degree which is less than the integer part of the okay. So if u of x is less than constant 1 over x to the alpha, then u is constant. If alpha is in between 0 and 1, and if you increase alpha, then you find a polynomial solution. Of course, if u does not depend on y, and it depends only on the x variables, then this will always, and it is harmonic, will always be a solution of this problem. Okay, so with the Liouville type theorem, we obtain regularity estimates. Okay, now, how much time do I have? Not much. Okay, now, Murdoch lemma as a Liouville type theorem, and this is very nice. Okay, and this can be used. Okay, so let's try to rephrase, and if you like, you can also try to help me. Okay, so now we call So this means that P over Q is a polynomial. Okay, so Q is our U, P is our V, and W is our Q over P. Okay, which being a polynomial is as much regular as we like. Okay, so now we wish to so now we have this other theorem which says, okay, now let W solve this equation, U squared that W is equal to 0 on Rn. W is continuous. This is not granted by the equation. Okay, W is V over U. And assume where U is a harmonic polynomial. Okay, and assume that W grows less than some power, whatever power. Okay, W of x less than 1 plus x to the any power alpha. Okay, whatever alpha. Then W is a polynomial. Sorry, yeah. Then W is a polynomial. Of degree less than the integer part of alpha. In particular, if alpha is smaller than 1, then W is constant.
Okay. Excuse me. In this Murdoch lemma, if do we assume that the polynomial P is harmonic?
The Murdoch lemma, we only assume that Q is harmonic and P is not. Does not need to.
This equation for W.
No. In this is not equivalent. In fact, W is here we are assuming that also P is harmonic, but we are not assuming that is a polynomial. We are just saying we take any function. In the end, is also a polynomial because has an algebraic growth at infinity, and a harmonic function having such a algebraic growth at infinity is a polynomial. Also, so actually, but in this theorem is the transposition of Murdoch lemma in the case when also P is harmonic. Okay, but the Murdoch lemma is more general. Does not need that the denominator is harmonic, only the numerator. Okay, so with this in our hands, okay, we could prove uniform bounds of W, let's say, which is actually equal to the quotient in Hölder space. Okay, which are uniform with respect to what? Which are uniform with respect to the nodal configuration of U, okay, having a bound on the vanishing orders of U in the domain. In Hölder spaces, in a class where the vanishing orders of U in, let's say, in the zero set of U is bounded. And this can be expressed in terms of the Algebraic frequency formula, which has an upper bound and which also gives some compactness within this class. If we are in 2 dimension, this is equivalent to prove that the number of connected components, nodal components of U, is bounded. Oh, okay, in 2 dimension is maybe easier to be seen. And when we go, okay, so now we are kind of satisfied of Hölder bounds when the exponent A is equal to 2. So now we have a few minutes to say a couple of words about what happens when the exponent A is not is not 2. Let's say, let's start from 0, there was minus 2. Or we wish to go from C0 alpha bounds into C1 alpha bounds. So we wish to have the quotient not only be continuous, Hölder continuous up to the nodal set, but to be C1 with continuous derivative, Hölder continuous derivative up to the boundary. And here there are, let's say, several problems. The first problem is that we don't have a nice Liouville type theorem when the exponent is different from 2. Okay, because we actually derived this theorem by the Murdoch lemma, from the Murdoch lemma. So in general, we can say, okay, what can we say about solutions of this type of equation? Okay, which are in Rn and which are continuous in Rn. And A is whatever, let's say, maybe larger than 0. Just to say, okay, if it is 0, we know everything. Okay, when we have some information on the growth of W at infinity. Okay, can we say something? And in fact, we can say something, but only in dimension 2. Okay, if n is equal to 2, we have, in fact, the very same Liouville type theorem. Okay, we have Liouville type theorem. And from which are in fact independent of A, from which we also have C1 alpha estimates, which are not uniform with respect to the same class of bounded vanishing order function. Okay, what is nice here is that, okay, we do have solutions of this equation in 2 dimensions. Okay, why? We take a harmonic function and we take its harmonic conjugate. Sorry, here we also have that U is harmonic. We have to add this. Okay, so if we take if we take a harmonic function and a pair of conjugate harmonic function in 2 dimensions, then for any A, this equation will be solved. Okay? And so the problem is to prove that, in fact, these are more or less the only solutions of this problem, up to some possibly higher order term, which is kind of cancelled away in the large scale analysis. Okay, so sorry for this maybe a bit off topic seminar, and thank you for your attention.
Are there questions?
You mentioned that it would be possible to do something similar for not harmonic functions, but eigenfunctions. But what about this trick with double?
Okay, no, but this is okay. This it's a bit related with the way you do prove these local bounds in C0 alpha or C1 alpha. You do by contradiction, and then you scale out, and all the terms which are perturbation of the Laplacian just disappear. And you find in the limit of the blow-up something which solves, which is an entire or semi-entire solution of some elliptic problem. And then you are led to classify all the solutions that you can, and especially you are happy when you prove that there are no solutions, because this would give you the desired contradiction.
Other questions? No, thank you again.